Welcome back to ECE 220. If you're in section I, this is the week. Tomorrow is your lab. Make sure you show up with a cat card, something to take notes with, and closed-toed shoes. Also happening tomorrow is homework number 3. That's due. And Group A, which is sections E, F, G, and H, your pre-lab is due this Saturday. Your pre-lab for lab number 1 is due the Saturday before you execute your lab or go into lab, and you will start executing or performing lab number 1 next week. That's Group A, which consists of sections E, F, G, and H. Section I has your orientation lab, lab 0, tomorrow. All of that will be happening at the same week as homework number 4 is due, which we're talking about material for homework number 4, and you have your exam next Thursday. Your first exam is next Thursday. Most calculators are allowed, and if you want practice, I would recommend you look at some of the older exams that are linkable on the course website in D2L. And I'm guessing that this exam, exam number 1, will be similar in structure or format and content to what are those practice exams. Today, what I want to do is finally get to this question: does it matter where or how we select the reference node? We'll go through an example to try to illustrate that. Then we will look at and review and generalize, really, Kcl. Kcl not only applies at a particular node, but if we create a closed boundary around nodes or a section of a circuit, Kcl works with that as well. We can then figure out what's going in and going out, or we can say what's the algebraic sum of the currents relative to this closed boundary. And that's going to be instrumental in allowing us to work with supernodes, which I hope we get there. But we have a couple of examples I want to work through before that. But then we will get into supernodes, and supernodes really occur when we have a voltage source, and that voltage source could be an independent voltage source or a dependent voltage source between two essential nodes. If we have a voltage source between two essential nodes, we really don't know what the current is in terms of those essential nodes, because the supply is going to produce whatever current is necessary. We'll look at how we examine circuits with supernodes, and we'll illustrate why it's okay to apply this concept with our first supernode example, and then we'll have another supernode example. That's the optimistic goal set for today. Hopefully we will get part way or most of the way through that. Let's start with the selection of the reference node, and does it matter? Here's a circuit, and I haven't really labeled too much other than I have some current sources. Everything is independent. All my sources are independent because they're circles. There's some resistors. How those are labeled doesn't really matter for this discussion. What I want you to identify now are the essential nodes. Where are the essential nodes in this network? Can you see them, or can you identify them? That's something that you have to quickly be able to simply execute or perform when analyzing circuits, especially node voltage analysis. Hopefully, you see that here is an essential node, Is this an essential node? No, it's only connecting two circuit elements. Here is an essential node. Here is an essential node, and this is an essential node. And the significance of these essential nodes, their size, the way I've diagrammed them, is not that critical, but sometimes it's helpful actually to assign your reference node as the one where most elements are connected to. Sometimes that's beneficial, and that sort of is then consistent with this larger graphical circling of the bottom nodes. Let's label these so that we can play with them in a minute. Here's A, B, C, and D. And suppose we say, let's let the reference node in this circuit be D. Right below this circuit is its twin. So let's just identify the essential nodes for it again. There's A, B, C, and D. But in this version of the exact same circuit, let's go ahead and let B be our reference node. Now, what I want to do is illustrate that the voltage difference between these nodes, or between our nodes in the circuit, will be the same. Now, to do that, let's go ahead and label these in the two different circuits distinctly relative to the reference nodes that have been selected. Suppose that in this particular circuit, I call this potential difference between B to the reference V sub 1. I have to now, with the remaining essential nodes, that remaining meaning the ones that are not the reference node, I now need to identify the node voltage to those essential nodes relative to the reference node. Here is one such node voltage, V sub 1. Another one could be this node voltage, V sub 2, from C to D. And the last one is going to be this one, from A to D. I have three node voltages relative to the reference node that I've now identified. If we do something similar in the twin, now let's use different labels for these because we have a different reference node. Let's use V4, V5, and V6, and so that my discussion matches my prepared material, let's say that the first one, V sub 4, is from C to B, that node voltage. Meaning, here's V sub 4, and I now, if I was in the lab measuring this, I would put the red lead, the positive lead, on node C, and the ground lead, or the common lead, would be on B. And I would measure V sub 4. V sub 5, let me just let that be from A. That looks kind of weird, doesn't it, to have two negatives? It makes it look equal. So let me just, those are both relative to that point. They're going to share the same common node. There's V sub 5. That's A relative to B. And we have one more, which is D relative to B. Let's call that V sub 6. This is now, I would put my positive lead on D, and my common lead, my black lead, on node B, since that's the reference node in this twin circuit. What I'm suggesting in this discussion is that the potential difference which is really just the voltage across each pair of nodes is the same in each circuit. It's the same circuit. Now if I measured the potential difference between A and B, that better be the same in both circuits. It's exactly the same circuit. But I've labeled them different because I have a different selection of the reference node in each particular network. Now, relative to this circuit, what's the potential difference between nodes A and B? What's the voltage dropped from node A to node B? How would I write that relative to these node voltages? If I want to know what's the voltage from node A to node B, how would I express that in this circuit? How would I write the voltage drop from A to B? If I was measuring the voltage drop from A to B, and I actually knew V1, V2, and V3, could I, on a piece of paper, calculate that voltage drop before I measure it? If I'm given V1, V2, V3? Isn't it just V3 minus V1? That's the drop from node A to B. So let me write that down. This is now from A to B in the first circuit. Here's the top circuit. That was V sub 3 minus, what was it? V sub 1. What if we do that in the bottom circuit? Here we're going to say equal to. That's what we're suggesting. In the bottom circuit, what's the potential difference between A and B? That's one of our node voltages. It's V sub 5. Or we could say V sub 5 minus 0, which is what we're assigning to node B. A to B is now V sub 5 minus 0. What about if we wanted the drop from A to C in top and bottom circuits? A to C. What's that? V3 minus V2. What is it here? What was I saying? From A to C. V sub 5 minus V sub 4. What about A to D in the top circuit? Are you getting the hang of this? If you now need to find the voltage dropped from A to D, that's V sub 3 or V sub 3 minus 0. 0 is the potential we're assigning to the common node or the reference node. This is now V sub 3 minus 0. And in the bottom circuit, the drop from A to D, V sub 5 minus V sub 6. Pardon? Are we ever adding the voltage drops together? Not in this scenario, because we're trying to find the difference between two nodes. And we've assigned each of those essential nodes relative to a reference. We're comparing their difference. We're saying, what does it take to go from A to B? That's the potential at A minus the potential at B. Likewise, now let's just keep going. I'm having so much fun. I'm sure you are too. B to C. What is B to C in the top circuit? And you need to know this or be able to do this when you're writing all these Kcl equations when we do node voltage analysis. This is V1 minus V2. And in the bottom circuit, what am I doing? B to C. It's now 0 minus V4. If you want to take something away from something, now you're taking V4 away from 0, which is our reference node. This is now 0 minus V sub 4. B to D. That one's easy. That's V1 minus 0 in the top circuit. And in the bottom circuit, B to D. 0 minus V sub 6. Finally, C to D. V2 minus 0. And C to D here. V sub 4 minus V sub 6. How many equations do we have? We have two circuits. We have three essential nodes in each circuit. They're labeled completely different. But let's say that we now knew from the top circuit V1, V2, and V3. And somebody goes, yeah, that's not how I labeled my circuit. I labeled it like the bottom. I need V4, V5, and V6. You go, not a problem. We know linear algebra. We have three equations. You have your three unknowns. We can pick any three of these 6 equations and solve for your three unknowns, V4, V5, and V6. Because these 6 equations were independent of each other. They're not telling us the same thing, each of these 6. So we just need to pull 3 of these and solve for V4, V5, and V6. What if we took the top 3 equations? Not they're rated the top, they're just the first 3 that we did. But here what I'm saying is 3 equations and 3 unknowns. We can pick 3 of the above 6 equations and solve for V4, V5, and V6. Suppose we pick A to B. Well, now, do you see that we can actually write this in a matrix form? This is why it's so important to know linear algebra. You'll get it next year if you aren't doing it now. Some of you are taking a math class, linear algebra. We're trying to solve for V4, V5, and V6. Let's put that in our, this is really just, I've got too many A's floating around, too many C's and B's, but this is AX equal B. This is the math form, so let me put that kind of in quotes. That's not the same, that's not node A, this is matrix A. And now I'm saying I want to solve for X, which is V4, V5, and V6. Let me write the first equation, A to B. Now I want something that involves V4, V5, and V6, which is really the right-hand side up here, I need to pull off V sub 5 in this expression, and I can do that by multiplying that unknown vector by 0, 1, 0. That identifies or isolates V sub 5. And based on this first equation, that's equal to V sub 3 minus V sub 1. Those I know. I'm saying I know V1 through V3. So I know V sub 3 minus V1. And now we know what V sub 5 is. V sub 5, I just subtract V1 from V sub 3. But let's now look at the next one. B to C. Put that in this matrix form. Whoops. Sorry. I said A's were wild. So A to C. We started with A. We now want to put this into that structure. What do we put in the second row of that, quote, A matrix? Whatever we put in that row needs to end up, when it's multiplied by a V4, V5, V6, needs to produce V5 minus V4. I can do that by V4 minus V5. So what is this first matrix? This first matrix is really just trying to produce the linear combinations of V4, V5, and V6 that we're trying to identify from this right-hand side. And we're just picking 3 of these equations to try to show that you can actually find V4, V5, and V6 from any of these if you know V1, V2, and V3. The first row in that matrix was determined by the AB relationship. The second row was the second row, and the third row in that matrix is now going to be V sub 5 minus V sub 6. And that's equal to, whoops, I didn't complete the second row. What's the second row? A to C, that's V sub 3 minus V sub 2. And this is now the A to D relationship, which is now equal to V sub 3. If I solve that for V4, V5, and V6, you could now invert that matrix, or you could just do simultaneous solutions, and you'll find V5 is V3 minus V1. V4 ends up being equal to V2 minus V1. V5 was V3 minus V1 from the very first row, and V6 actually just ends up being minus V1. So this is the solution that you would produce for your buddy if you had V1, V2, V3, and they had their circuit labeled as V4, V5, V6. Now here's the fun part. Now you go home and you pick another set of those 3 equations. What's going to happen? You're going to get exactly the same answer that we obtained in that first iteration or first combination. So even though the A matrix and the B matrix will be different, the X will be the same. In terms of V4, V5, and V6 will be exactly the same as what we computed from this. Remind me what we were trying to do here. What was the point of this exercise? It doesn't matter how we select the reference node. All the potential difference between these nodes will be the same no matter how we label them initially. That was the point of this linear algebra exercise. If the linear algebra was throwing you into a fit, don't worry, we aren't going to do too much of that. We'll just get into 10 by 10 matrices next week. No, just, yes?
Could we use either one of those circuit equations to solve for everything though? Or do we need both? Would we need both of them in any situation?
So the question was, if I've now I think this is the question, I'm going to paraphrase it. If I've now labeled my circuit this way as the top circuit, can I get all the answer or the information I need without doing the second circuit? And the question is yes. Or if you had labeled your circuit like the second circuit, you could get all of the information. You could find all the currents, all the powers, whatever you need from that circuit based on how you had labeled it in the bottom circuit. And all of those should be consistent. If somebody now finds out that the power associated with one of those resistors is a certain value, the way you analyzed it, you better get exactly the same thing. Your voltages and currents may be labeled differently, but all of your information should be consistent. Bottom line, it doesn't matter how you select the reference node. Now, on an exam, you may be forced to live with however the exam creation has selected a reference node. Yes? So now if we had 5 reference nodes, would we have a 5 by 5 matrix? How many reference nodes, or what essential nodes? Essential nodes. Woo! Started going 5 reference nodes. That would make the problem easy, wouldn't it? Everything would be 0. So we can't do that. We have 5 essential nodes, and playing with this, how many essential nodes did we have? 4. We pick one of those as a reference, and that now gives us 3 unknown essential nodes. We started with 5 essential nodes. We would get rid of 1, and we would have a 4 by 4 matrix if we wanted to do that way. So we would need 6 essential nodes to get to a 5 by 5. So next week, when we get the 10 by 10 A matrix, in quotes, we need how many essential nodes? 11. Okay, I'll be all weekend trying to create that circuit. Not. Let's now review and generalize KCL. KCL applies at any closed boundary. So the circuit below identifies several closed boundaries indicated by this dashed red loop or boundary. And we want to now assume all of these equations are written in terms of we're summing currents out of the node. So let's now, here's the circuit. Should have showed you that so you have time to draw it if you don't have the prepared notes. Now I've enclosed or created closed boundaries in this circuit. Several of those, 4. And they're not all essential nodes. These are just closed boundaries. And I've identified 5 different currents that I want to use in relating or connecting Kcl equations for these 4 locations. And I'm going to use the strategy that I'm going to be summing currents out of nodes and setting those sums equal to 0. That's one way to express KCL. Sum of the currents leaving a node equals 0. What about now if we write down the sum of the currents leaving I? Here I have I in quotes. That's referring to the enclosed set of branches to the right. How would I write that expression? And let's try to, I guess, maybe start with the lowest subscript. Whoops. Current. I want to sum the currents out of that node, labeled as I. How would I do that? What's the Kcl equation for that? I think I1's leaving, isn't it? Is I2 leaving? So I add that. What about I sub 5? If that confuses you, you could say, well, this is a current that's leaving, and that's opposite to the way I had originally labeled it, so that's minus I sub 5. So I sum that in, and those are my three currents that leave that enclosed or closed boundary, and I set those equal to 0. These Kcl equations, you need to just be able to do those in your sleep. What about node 2? That's at the bottom, and this is actually a supernode because it's a voltage source that's connecting two essential nodes. What's the Kcl equation at 2? Starting with the lowest subscript current. I see an I sub 2. Is it leaving as drawn? No, so this is now minus I sub 2 plus I sub 3 plus I sub 4 plus I sub 5 equals 0. That's Kcl 2. And actually, maybe I shouldn't have said that. I just had 30 students fall asleep. Well, you said we could do this in our sleep. So, okay, yes you can. But pretend you're awake. And now let's do 3. What's Kcl for this closed boundary? Is I sub 3 leaving? Wait, I need to start with I1, don't I? All of these are coming in, so they're all going to have negative signs. This one is now minus I1 minus I3 minus I4 equals 0. And finally up to 4, what's that Kcl equation? Coming in from the left, and then that has to algebraically combine with the current coming up from the bottom. Oh no, I'm summing out, aren't I? I said sum of the currents out. So I sub 1 is not going out, minus I1 is. And what's leaving the vertical wire? That's why we don't worry about those kinds of nodes when we write Kcl. It's not giving us very useful information. It just says 0 is equal to 0. Duh. We have a node and a wire going in and out of that node. The current coming in is going to equal the current coming out. But we can still write KCl. So KCl at a circuit node is the most commonly used application. That's example I. So you better be able to do I. And if you now labeled those appropriate essential nodes or node voltages, you could write I1, I2, and I5 or minus I5 appropriately. Let's practice that. Suppose now somebody's given you this circuit and they say find the power associated with the 100 volt source. And I have this 62 volt independent voltage source. First step, find essential nodes. Here's one. Here's one. There's one. And what do you think I'm going to select for my reference? The biggest cloud? We're playing with clouds again in this class, so if somebody says, are you dealing with the cloud in 220? You can say yes. Cloud influences our node selection. In this case, let's let that be our reference node. And just working from left to right, let's call this V1 and this V sub 2. Have I found everything? Have I identified all of the appropriate pieces to analyze this circuit? If I'm trying to find the power of that 100 volt source, I might be interested in the current flowing through that, right? In addition to the voltage. What if I labeled this as I100? Does the direction matter for what? So now does it matter the direction of I? Just if you need to keep track of things, you need to make sure you stick with the labels that you've assigned. But as long as you use the passive sign convention and stick with the labels that you've assigned, you should get exactly the exact answer that you need. It doesn't matter which direction you pick. Here, though, with KVL, we're usually thinking of that current going from right to left through that 20 ohm resistor. So let's just label it as I100. And if I have I100, then I can find P100. That's going to be with the passive sign convention. What's the expression going to be? What's the power using the passive sign convention for that source, 100 volt source? Isn't it the voltage times the current? And which way is that current directed? Is it hitting the positive label before it goes through the element? This now needs to be a plus in front of that, which means that this power is now absorbed or consumed when we find it. If we use this labeling, if we find I100 and use it, whatever sign it ends up with, then that product is going to give us the power absorbed by that 100 volt source. If that 100 volt source is in fact delivering or supplying power to the rest of the circuit, we would expect I100 to be negative. Just that's on the side of our paper. But now how do we find I100? Can we just write that down? Do we know it? I100 was not given. It's now going to have to be determined by analyzing this circuit. Could we find I100 fairly quickly from some of these labels? If we knew V1, I could find I100 pretty fast. Wouldn't I1 or I100 be V1 minus 100 divided by 20? I just need to find V1. Well, that means I need to do some node voltage analysis. I need I100 to find the power that I'm after. And if we had V1, then we could find I100. I100 is just V1 minus 100 divided by 20. And if we now start doing our node voltage analysis, step 1, we've already done. We've identified V1 and V2, our node voltages in this node voltage analysis process. Step 2. Write the equations that will allow us to determine V1 and V2. Let's write KCl then at node 1. Here's node 1. Here's node 2. KCl at node 1. Let's just look at the currents going out. That's V1 minus 100 divided by 20. That's going to the left. Going down, V1 divided by 80. Going to the right, that's kind of a mess because we have that voltage source, but we could make our life maybe a little less difficult if we just called that V sub x. Then it would be V1 minus V sub x divided by 40. And we know how to find V sub x relative to the voltage source and our node voltages. I'm just going to do a KVL eventually to find V sub x. What did I just try to write down? I said KCl at node 1 is now V1 minus 100 over 20 plus V1 over 80 plus V1 minus V sub x over 40. And that's equal to 0. And using a KVL equation to find V sub x in terms of V1 and V2, and given information, minus Vx minus 62 plus V2 brings me back to ground. I now know with a KVL that I have minus V sub x minus 62 plus V sub 2 is equal to 0. Or V sub x is equal to V2 minus 62. And this can be used up there. So that now this V sub x I'm going to replace with v sub 2 minus 62. And now I have one equation and two unknowns. I'm going to try to find my next equation. Well, let me clean this up a little bit. If I multiply everything in that equation by 80, I'm going to clear the fractions. So if I multiply everything by 80, I will end up with 4v1 minus 400 plus v1 plus 2v1. Now I have to remember what v sub x was. I'm subtracting v sub 2, but that's getting scaled by 2. And I have a minus 62. That's a plus 62 times 2. Luckily 60 I can double. That's 120, and I can double 2. That's 4. This is now plus 124. I can collect all of those common terms. I have a 4v1, another one, and 2. That's 7v1 minus 2v2 equal 400 minus 124. So if it was 125, I would know I have 2 3/4. So I'm a little bit bigger than that. I'm now 276. So there's my first equation in two unknowns, from writing a Kcl equation and the constraint equation connecting that source that was between my two essential nodes. Now I can write Kcl at node 2. What's going to the left out of node 2? What current? What's the equation? I don't know, that source is messing me up. Well, the same current going through that source is going through that 40 ohm resistor, and that 40 ohm resistor has a current of V sub x minus V1 divided by 40. And we already know an expression for V sub x. Then we have 2 amps coming down and V sub 2 divided by 4. Kcl at 2 now says V sub x minus V sub 1 over, what was that resistor? 40 plus 2 plus V sub 2 over 4 equaling 0. And we already know what this is. This V sub x is V sub 2 minus 62. And if we scale this one or multiply everything by 40 here, I'll clear those fractions. And I now end up with V sub 2 minus 62 minus V1 plus 80 plus 20 V sub 2. No, I'm multiplying by not 80, 40. 10 V sub 2 equal 0. I couldn't do that in my sleep, could I? Up here sleeping. Now let's clean that up. We have V1 minus, how many V sub 2's do we have? 11. And what's on the right hand side? Our constant is over there. And that's now 62 minus 80, or that's now minus 18. This is now our second equation. Whoa, I'm out of space. I now need to solve these two equations simultaneously. And the easy way to do that might be to multiply this one times 7, this bottom one, so that it now becomes minus 7v1 plus 77v2 equal 18. That's now 70 plus 56, or 126. Now I just combine those two equations. I add them. And I get rid of my v sub 1. I'm solving two equations in two unknowns. Doing that now gives me 77 minus 2, that's 75, v2 equaling 276, and this was a minus, sorry, minus 126, or that's now 150. And we end up with v sub 2 is equal to 2, and v1 we can use from that box. We'll figure that out. I'll do that offline, somewhere in the cloud probably, and you guys will see you tomorrow.